Hello, I'm reporter number 8. Welcome to the last section. Under chapter 4, we have the Probléme de Ménages, or it is also called the Ménage problem. This is in connection with the chapter, the principle of inclusion and exclusion. So for the definition, Probléme de Ménage, in French, ménage means married couples. So it asks for how many ways are there to seat unmarried couples where n is greater than or equal to 3 around a table such that men and women alternate and each woman is not adjacent to her husband, or nobody sits next to his or her partner. This famous problem was raised and popularized by Edward Lucas in his book published in 1891. In fact, an equivalent problem was first posed by Peter Gottfried Tite much earlier in 1876 and was settled by A. Cayley and T. Muir independently in 1877. So in this section, we shall apply Theorem 4.3.1, which is the GPIE, or Generalized Principle of Inclusion and Exclusion. This was discussed prior to this. To solve the above problem in a more general way. Before doing this, let us first study a problem due to I. Kaplansky. A brief recapitulation for GPIE. It states that let S be an n-element set and let P sub 1, P sub 2 up to P sub q be a set of q properties for elements of S. Then for each m is equal to 0, 1, 2 up to q. So we have here example 4.8.1. Suppose that the numbers 1, 2 up to m, where m is greater than or equal to 3, are placed in order around a circle. For k is greater than or equal to 0 but less than or equal to m over 2. Let alpha quantity k denote the number of k element subsets of n sub m in which no two elements are adjacent around the table. Show that alpha quantity k is equal to m over k minus 1 up to m minus k minus 1. So for instance, if m is equal to 10 and k is equal to 4, then set 1, 3, 6, 9 and set 3, 5, 8, 10 are such subsets, while set 1, 6, 8, 10 and set 2, 6, 7, 9 are not. Note that if m over 2, rather k is greater than m over 2 but less than or equal to m, no such k element subsets can exist. When k is equal to 3, example 4.8.1 is the same as problem 1.34 in the previous discussion. So if the term circle is replaced by row in example 4.8.1, the problem is identical to that in example 1.5.3. This example was discussed prior. It was the injection and bijection principle. So here's the illustration for this example. So let's go to proof. For each I is equal to 1, 2, up to m, let alpha sub I denote the number of such k element subsets of n sub m which contain I. By symmetry, alpha sub 1 is equal to alpha sub 2 is equal to up to alpha sub m. We now count alpha sub 1. If B is such a k element subset of n sub m containing 1, Then by the hypothesis 2, M is not an element of B, and thus the remaining k minus 1 elements of B must be chosen from 3, 4 up to M minus 1, such that no two are adjacent in a row. So hence, by the result of example 1.5.3, we have alpha sub 1 is equal to k minus 1 up to m minus 3 minus k minus 1 plus 1 is equal to k minus 1 up to m minus k minus 1. And so we have this summation. So it follows that we have alpha quantity k is equal to 1 over k, the summation of I is equal to 1 up to m. Alpha sub 1 is equal to m over k times the quantity k minus 1 up to m minus k minus 1. So this is the end of the proof. We are now in the position to establish the following result. So next we have example 4.8.2. There are n married couple where n is greater than or equal to 3 to be seated in the 2n chairs around a table. Suppose that the n wives have already been seated such that there is one and only one empty chair between two adjacent wives as shown. So we have this illustration. So we have to let m times n r, and let r is greater than or equal to 0 but less than or equal to n. Denote the number of ways to seat the n husbands in the remaining chairs such that exactly our husbands are adjacent to their own wives. Show that. So we have this equation. So for the proof, let S be the set of all arrangements of the n husbands, h sub 1, h sub 2 up to h sub n. We define 2n properties, p sub 1, p sub 2 up to p sub 2n, as follows. So an arrangement in S is said to possess the property. So we have this. P sub 1, if and only if husband 1 sits to the right of his wife. So we have W sub 1. So P sub 2, if and only if husband sub 1 sits to the left of his wife, W sub 1. We have P sub 3, if and only if husband 2 sits to the right of his wife, which is W sub 2. P sub 4, if and only if husband 2 sits to the left of his wife, W sub 2 up to P sub 2 n minus 1, if and only if husband n sits to the right of his wife, W sub n. P sub 2 n, if and only if husband n sits to the left of his wife, W sub n. So it is important to note that P sub I and P sub I plus 1 cannot hold the same time, for each I is equal to 1, 2 up to 2n, where P sub 2n plus 1 is defined as P1. Thus, we have here omega times Pi plus 1 is equal to 0 for each I is equal to 1, 2 up to 2n. If we arrange the 2n properties in order around a circle, as shown here, this one, then by the first equation, if the k-element subset P sub I1, P sub I2 up to P sub 1 sub k contains two adjacent members around the circle. So this implies in particular that, number 1, for k is greater than n but less than or equal to 2n, we have omega p sub 1 sub 1, we have p sub 1 sub 2 up to p sub 1 sub k is equal to 0, and so omega times k is equal to 0. And for 2, we have for k is greater than or equal to 1 but less than or equal to n. So we have this equation. So n minus k here, or the factorial of n minus k, denotes the number of ways to seat the remaining n minus k husband, multiplied with this by the theorem 4.8.1. So finally, we have this equation. So omega times k is equal to the summation of m and r, and it is also equal to E times the quantity r. So it is shown here, the equation by GPIE, or the general principle of inclusion and exclusion. So by 2 and 3, we have this final equation, so as required, end of the proof. The case when r is equal to 0 gives the solution to the Probléme de Ménages. The formula for this special case is this one. It was already shown in 4.8.3. It was discovered by J. Touchard in 1934. The idea used in the above proof is due to I. Kaplanski. For a different proof of formula 4.8.3, but still based on PIE, the reader may refer to Bogart and Doyle. For simplicity, let m sub n is equal to m and 0. Two intersecting identities involving m sub n's are given below. So we have n minus 2 times m sub n is equal to n times n minus 2 times m sub n minus 1 plus n, m sub n minus 2 plus 4 times negative 1 to the power of n plus 1. We have this summation where m sub 0 is equal to 1 and m sub 1 is equal to negative 1. So as pointed out in Kaplanski, the following limit follows from identity. We have this limit. To end this chapter, we give in table 4.8.1 the values of m sub n for n is greater than or equal to 2 but less than or equal to 10. So we have this table 4.8.1. So this ends my report. Thank you for listening, and may God bless us all. Mga problema na.